All right, we're going to go through some notes that are not on PowerPoint. All right, first topic is going to be what happens when you add reactions. So equilibrium constant. For the sum of reactions. All right, so you're going to have two reactions, and these are going to have equilibrium constants. They are not going to be step one, step two. It is just going to be two reactions. This is not a mechanism. This is just two reactions that we're going to add up. Just like when we did Hess's law, we added up reactions. We're going to do that for our equilibrium constants as well. All right, but it's going to have a little bit of a different twist to it. All right, so CO plus 3H2, and these I'm just going to put all gases. All right, so everything here is a gas. I'm not going to write gas after each one. That's important because that's part of your equilibrium constant Kc. CH4 plus H2O, and that's the key one right there. H2O here is a gas. All right, and so Kc for this first reaction has a value of 3.92. All right, the second reaction is CH4 with 2 H2S in equilibrium with CS2 and 4 H2. And the Kc for this second reaction is 3.3 times 10 to the fourth. All right, and so it's going to say add the reactions and give the K value for this reaction. All right, and so we have to then subtract 1 CH4 from both sides. We will subtract 3 hydrogens from both sides. That gets rid of all 3 of these. And then 1 remains on this side. And so when you bring it down, you have your CO, you have your 2 H2S in equilibrium with your CS2, your H2, and your H2O. All right, and then the question is Kc. That is the question. What is the answer for Kc? All right, so you have to know what to do with your K values when you add reactions. All right, so let's do the expressions. We're going to do all 3 expressions. So expression for Kc1. So that's the concentration of CH4. It was stated that they're all gases, so they are all going into our expression. H2O concentration divided by your concentration of CO and your concentration of H2, hydrogen gas, raised to the third. All right, and then we have a value for that. It's 3.92. I just wanted the expression. All right, so the expression for Kc2 is the concentration of products, CS2, concentration of H2 raised to the fourth, divided by the concentration of CH4 and the concentration of H2S raised to the second power. All right, Kcs, whenever Kcs are given, they will never be given with units. Sometimes I will ask, what are the units? All right, and so if I ask what's the units for Kc1, you would see that you have molarity times molarity. So in the numerator, you would have molarity squared. In the denominator, you have molarity times molarity to the third. That is molarity to the fourth. And so we cancel out 2 of them, and we are left with 1 over molarity squared. And so the units here will not be put. If I ask for them, you determine that to be 1 over molarity squared. All right, if we're doing the units for KC2, you have molarity times molarity to the fourth. You have then molarity to the fifth. In the denominator, you have molarity times molarity squared. You would have molarity to the third. So all three of those are gone, and we're down to molarity squared. All right, we can do the expression for the overall reaction when we added those two up. So the Kc for the addition of those two reactions, concentration CS2, concentration H2, concentration H2O over the concentration of CO, and the concentration of H2S raised to the second power. And if we're doing the units for that, we have molarity times molarity times molarity. That would be molarity to the third. On the bottom, we'd have molarity times molarity squared, also molarity to the third. And we see that they would completely cancel out. And our units for our Kc, when we add the two reactions, will be unitless. All right, so every other time that we've added up the reactions with the delta H's, we added the numbers. All right, and that is not what we're going to do here. And you can see that by the units. When you add numbers, our delta H's all had kilojoules per mole plus kilojoules per mole gives you kilojoules per mole. When you add numbers, they have to have the same units. These units are not the same, and even if they were the same, it would not be the way to do it. All right, but clearly not the way to do it in this case, because you cannot add a 1 over molarity squared plus molarity squared. You cannot do that. That is two different units. When you add numbers, they must have the same units. We know that when we get our answer here, it's going to be unitless. All right, so there's a lot of things that will show you that if you take 1 over molarity squared and you multiply it by molarity squared, you get a unitless number. And that is the answer to that's the answer to the question. When we want to get our equilibrium constant, when we add reactions, we multiply the K value. So it is Kc1 times Kc2. You can also see that is if you multiply the two expressions together. All right, so you would see that the CH4s would cancel. All right, and so CH4 does not show up here. You also see that your 3 hydrogen to the third would cancel out completely, and you would be left with hydrogen to the first in the numerator. All right, and so you can see when you multiply those two expressions, this is the expression that you will get. All right, so if you forget that you multiply your K values, you can figure it out mathematically by multiplying your two expressions and getting the overall expression. Therefore, you multiply the K values. So there will definitely be a problem when we're adding up reactions. And what's the new K value? So when you multiply those two numbers together, you get the answer 1.3 times 10 to the fifth. And so the answer to this question, what is the equilibrium constant for the sum of these two reactions? It is 1.3 times 10 to the fifth. All right, so the next question is going to be, all right, so the next question, I don't want to go that far. I want to take that second reaction. All right, and I'm going to do this to the second reaction. I'm going to take the CS2 plus the 4H2 in equilibrium with CH4 plus 2H2S. And I want the Kc value for that. All right, well, we see that it is our second reaction, our Kc2 up here, except we reversed it. So remember when we had delta H and we reversed it, we just changed the sign of delta H. That is not what we're going to do here. It will be a choice in your multiple choice. That is not the right choice. the best way to see what is happening is to write the expression for Kc. The expression for the Kc for this reaction is CH4 concentration, H2S concentration squared over CS2 concentration, H2 concentration raised to the fourth. And you look at that setup and you look at the setup that you had before. All right, so here is the original Kc reaction and its expression. And here is now the Kc for this reaction after we reversed it. And so you see that the products are now reactants, the reactants are now products. We invert the K value. All right, and so you must know when you reverse a reaction, you invert your K value. All right, and so we grab our calculator and we invert the 3.3 times 10 to the fourth. And so your Kc value for this reaction is 1 over the Kc of the reaction 2. So you grab your calculator and you have 3.3 times 10 to the fourth, and then you invert it. And you get 3.0 times 10 to the minus 5. So this is equal to 3.0 times 10 to the minus 5. All right. So again, when you reverse a reaction, you invert your K value. Also note that you know what it means to have a large K value and a small K value. When you're looking at the original and you had a very large K value, that means that you're favoring the products. All right, so there's a lot more products than you have reactants. All right, when you invert it, you still have a lot of the concentration of the CS2 and the 4H2. That's what you have a lot of. But when you reverse it, now that large number is a reactant. And so that is why you get a very small K value when you invert it. So anytime you invert a large number, you're going to get a small number. All right, so if the forward reaction favors products, the reverse reaction is going to favor reactants. It's not going to favor products. So there's a lot more reactants here, very few products. All right, so when you have a small Kc value, remember, you're always doing, every time you do the setup, it's the concentration of your products divided by your concentration of reactants. So if you have a large K value, that means you have a lot of products. When you have a small Kc value, that means you have very few products and mostly reactants. All right, so that is going to be on the test. Make sure you know what to do with your K values. When you add reactions, make sure you know what to do to K values when you reverse reactions. Oh, okay. What else can we do with our K value? We can do this. I almost forgot. All right, so let's try it. Yeah, we'll just do this one. All right, so what if I had 2CS2 plus 8H2 in equilibrium with 2CH4 and 4H2S, and I want the Kc value for this reaction. All right, when we did our Hess's law, we manipulated our delta H reactions. When you multiplied through by 2, you multiplied the delta H by 2. That is not what is going to happen here. We show the expression for Kc for this reaction, and we compare it to the Kc before, and we will know mathematically what to do to get that number. All right, so now we have CH4 raised to the second power. We have H2S raised to the fourth power. And our reactants, we have CS2 raised to the second power. And we have H2 raised to the eighth power. And so when you compare the Kc up here to the Kc down here, you see that it has now been squared. If you square this, then that is a 2, that is a 4, that is a 2, that is an 8. All right, and so when you multiply through by an integer, you have to raise your KC to that integer. And so the KC here is equal to 3.0 times 10 to the minus fifth. And now we have to square it. And now we don't need a calculator for that. It is 9.0 times 10 to the minus 10. All right, and so you need to know that as well. If we multiplied through by 1/2, then we would have to raise it to the 1/2, which is the square root of that number. All right, so you have to know what to do when you add reactions. You have to know what to do when you reverse reactions. You have to know what to do when you multiply through by an integer or a fraction. Or you divide by an integer. That would be the same as multiplying by a fraction. All right. So make sure you know what to do with your K values when you are manipulating those reactions. All right, here's just another review to make sure you are aware to not just brainlessly write things down because they're easy, because then there will be a little twist. You have to think at all times in order to get the right answer. You may think it looks very easy, and it is, but it's easy to make a simple mistake. All right, so if you have this problem and it says give the expression for KC, it should be the easiest problem on the test. And so you're going to go too fast and get it wrong. All right, so make sure when you're writing the KC, you are very aware of the phases. The nickel here is a solid and will not be included in the KC. If this is a multiple choice question, one of the choices will have nickel in it. Do not pick it. It is the wrong answer. All right, and so it is your concentration of your products, all right, over the concentration of reactants raised to their coefficient. All right, so again, that is just an example of be aware of the phases. On the ones above, I made a statement, everything was a gas. All right, here it's going to be labeled for you on the test. The solids, the liquids, the gases, the aqueous. If you're doing KC, never put in a solid or a liquid. And if you have a question about your Le Chatelier's principle, all right, so you're at equilibrium, you add nickel, what happens? Not a single thing. It is not part of your equilibrium expression. If you added CO, well, then you have too much CO, so it has to go to the right in order to get rid of some of that CO, get back to balance for your KC. If you're adding NiCO4, now you have too much product, and it has to go to the left and form some reactant, get rid of some of your product. If you're removing CO, then you don't have enough CO, so it has to go to the left to form more CO. If you're removing your NiCO4, you don't have enough of it. It goes to the right to form more. All right, but if you're changing a solid or a liquid, that has zero effect on your equilibrium. If you add a catalyst, that also will have no effect on your equilibrium. All right, so now we're going to do, in the, when we did our quadratic equation, they did it a different way, and I did it their way and my way. The answers come out exactly the same. The way they did it is they divided by the 49.7, which made the number smaller instead of multiplying it by that and getting giant numbers. Either way, your calculator deals with big numbers or small numbers. All right, but we're going to have a way to do a problem. You can do it by the quadratic equation, or you can do it by what is called successive approximations. All right, so let's do this problem, N2 plus O2. All right, nitrogen is a gas, oxygen is a gas, and that's going to form 2NO, which is also a gas. And this has a Kc value of 4.6 times 10 to the negative 8. All right, and we're going to start with 0.010 molar and 0.010 molar, and we're not going to put any of the product in there. All right, and we're going to do examples where we have all three of them, and we're going to have to decide which way the reaction goes. When you have a zero, you can never have a zero when you are at equilibrium. And so we know that it's going to form some, maybe a small amount. Since our Kc is small, then this amount will be small, but it will not be zero. All right, and so we know it has to go to the right. So minus coefficient of 1x minus the coefficient of 1x plus the coefficient of 2x. So remember to put in the coefficient and then your x. All right, and so then at equilibrium, we're going to have 0.010 minus x. We're going to have 0, let's make this a 2. We're going to have a 0.020 minus x, and we're going to have 2x. And there's a reason why I changed it, because then there would be an easier way to do this than successive approximation if they were the same. All right, so you always should write your expression for the Kc. It is the concentration of NO squared over the concentration of N2 and the concentration of O2. Now, this is a Kc, which means equilibrium, which means only the equilibrium numbers can go into a Kc expression. If you're putting in different numbers, you would have the same expression, but it would be a QC. So if you're putting initial in, you can put that in on a QC. All right, when you're putting in equilibrium, that is a Kc. So we plug in what we have. We have for NO, we have 2x, and it is squared. For the N2, we have 0.010 minus x. And for the O2, we have 0.020 minus x. And we are given the value of 4.6 times 10 to the minus 8. All right, so this is a small Kc. What that means is we're going to have fewer products. So the amount that comes to the right is going to be a small number. So we know that x will also be small. So anytime your K value is small, your X value going to the right will also be small. So when we're doing successive approximations, all right, we are going to neglect X. So since we know that X is small, so we neglect anytime we have a plus or a minus X. So here we're going to neglect both of these X values, all right? So this is called successive approximations. All right, and so we're going to get what is then called an x1, and then we're going to get another x value and see if it's the same. If it is the same, we are done. If it is not the same, then we have to keep putting in our value for x. All right, so what we have now in the numerator, I'm going to multiply that out. A lot of people multiply this out incorrectly. 2x squared is 4. It is 2 squared and x squared. So it is 4x squared. Many people put 2x squared. That is the wrong math answer. All right, so we're neglecting the x. So we're saying it's going to be so small, it's not going to change anything. And so we are saying it's essentially 0. And so we're putting in a 0.010 for our N2, and we're putting in a 0.020 for our O2. And we know that that is equal to 4.6 times 10 to the minus 8. And so now we take our calculator, we take 4.6 times 10 to the minus 8, and then we multiply both sides by 0.01. We multiply both sides by 0.02. We divide both sides by 4. All right, and so when you do all that, after you've multiplied and divided, you have now your x squared is equal to 2.3 times 10 to the minus 12. All right, and so then you take the square root of both sides, and you get 1 point something times 10 to the minus 6. 1.5 times 10 to the minus 6. So we knew that x was going to be small. All right, so we're going to call this x1. All right, that may be our answer. We have to check it. When you do successive approximations, now you've got to plug it in here, and you have to plug it in here. So you have to plug in this number where it was neglected. And then get what we're going to call x2. So you plug in your x1 number and see if you get an x2. If x2 is exactly the same as x1, then you're done and that's your answer. If it is not, then you have to do that same process again until you do get the same answer twice. All right, so now we have 4x squared over 0.010 minus 1.5 times 10 to the minus 6. And we have 0.020 minus 1.5 times 10 to the minus 6. And that is equal to 4.6 times 10 to the minus 8. All right, so we take our 0.02. All right, so yeah, this is not going to change it. Okay, because that is, if you put this in decimal form, you were talking about 0.12345 zeros and then a 1 5. All right, so you see that when you subtract that from your 0.0200, you plug it in on your calculator and you get 0.199. How many nines? 1, 2, 3. And then an 8, 4, 8. All right, so if you're doing sig figs on this one, of course, it's not changing at all. But we will push the buttons to be certain, but I know for sure that the 1.5 times 10 to the minus 6 is not going to change the 0.02. All right, so we multiply that. 6, 8, 0.01 minus 0.5. All right, take the square root of that. And you get for x2, 1.5 times 10 to the minus 6. All right, so when you get the same answer twice, then that is the final answer. All right, this k value is very small. All right, so it's minus 8. All right, so when you get numbers that are not as small, like minus 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, it will take more than just the check to make sure it's right. It would take 2, 3, 4 successive approximations to confirm that answer. All right, so once you have that answer, I don't know that I put a question on this. I just said we're going to do successive approximations. The question is calculate the equilibrium concentrations. So that is the question. You're starting with 0.01 and you have 0.02. The question is calculate your equilibrium concentrations. All right, and so your equilibrium, when you take your 0.010 minus 1.5 times 10 to the minus 6, you get 0.010 molar. And so neglecting that x, saying that it is so small it's not going to change it, well, that was correct. All right, and so here you get 0.020 minus x doesn't change. When you subtract, we did that one down there, you got the 0.01999. Okay, when you have 3 decimals minus a bunch of decimals, 3 decimals, it rounds to 0.020. And then you have to multiply it by 2, so you have 3.0 times 10 to the minus 6 molar. So the 1.5 times 10 to the minus 6 times 2, 3.0 times 10 to the minus 6. And so your equilibrium concentration for nitrogen and oxygen is exactly the same as your initial concentration, because your K value was so small, very, very little came to the right, so small of an amount, it didn't change the initial amount using your 2 sig figs. All right, but NO cannot be 0. It's going to be a small number, 3.0 times 10 to the minus 6. That is a small number, but it cannot be 0. When you are at equilibrium, there are no 0 concentrations. There are very small concentrations, but not 0 concentrations. All right, so let's try another one that requires more than 1. Also, mathematically, x1, it will be your largest number that you have. When you do multiple, there's one in the homework that requires 20 successive approximations. A bit ridiculous. So there's not going to be any that require 20 on the test. But anyway, your first number is the largest, your second number is the smallest, and then it gets big and small and big and small and big and small until it gets to it is the same answer. If you use the quadratic equation, you will get exactly the same answer that you get when you do successive approximations. All right, so let's do another. Oh, and the reason why I changed my concentration was if these were the same concentrations, if this was 0.01 and 0.01, then you would have a perfect square. Then you can just take the square root and solve it that way. So the problems on the test are not going to be perfect squares. You could probably do the quadratic. That's a lot more math. There is going to be at least one that requires you to do successive approximations. And if you want to, you can check your answer with the quadratic equation. But the work shown must be the successive approximation showing your value for x1, x2, x3, x4, whatever number of x's, and when 2 are the same, then you have your final answer. All right, so let's do one where it requires more than one x value. So in this problem, we have PCl5, which is a gas, in equilibrium with PCl3, also a gas, and Cl2, a gas. All right, so the question, I'll write the question this time, calculate equilibrium concentrations. All right, and so the initial, all it says for the initial is we are going to put in 1 molar of our PCl5. And in this case, we have 4 sig figs for our 1 molar PCl5. We didn't put any of this in, and we didn't put any of that in. So again, we know which direction the reaction goes. You can't have a 0, you have to form some. And so your change minus the coefficient of 1x plus the coefficient of 1x plus the coefficient of 1x. All right, so at equilibrium, we're going to have 1.000 minus x. We're going to have x. We're going to have x, and the Kc is given. It is 0.0211. All right, this is a small number. All right, the definition of small is less than 1. All right, the very small numbers are the ones when you are in the minus 6, minus 6, minus 7, minus 8, smaller than minus 6. When it is minus 5, that's a little iffy. Minus 4, minus 3, minus 2, minus 1. Those will always require, usually require multiple successive approximations before you get the same number twice. All right, so this is small, and so that means that x is also small. So when your Kc is less than 1, then you know that your x is also small. So when your Kc is small, your x is small. And so anytime you are adding or subtracting an x, what you're going to do is you're going to say, well, this is a small number, and 1 minus a small number, it shouldn't change it. So we're going to neglect it. And if this was tiny, like 10 to the minus 8, 10 to the minus 10, you would be true, and you wouldn't really have to check it. Always a good idea to check it anyway. All right, so we have, again, you should always write your setup for KC, concentration, PCl3, concentration, Cl2, over the concentration of PCl5. All right, again, that is a K. You only put in equilibrium numbers into a KC. All right, so we have that number. It is 0.0211. At equilibrium, PCl3 is X. At equilibrium, Cl2 is X. At equilibrium, your PCl5 is 1 minus X. All right, and so we are then going to neglect that X. We're going to say it's small. So we're going to say, well, we're going to assume it's not going to change the 1. And so it's essentially 0. It's so small, it's not going to change it. And then we solve, and we're going to get X1. And so we end up with 0.0211 is equal to X squared divided by 1. All right, so you multiply both sides by 1. That doesn't change anything. All right, so we simply have to take the square root to get our X1 value, which is 0.145. All right, so now we have to plug this in where it was neglected. So this number has to be plugged in, not that far, right here. So plug it in. So plug in the number you get. Where you neglected it in a previous calculation, you plug it in. And so you have 0.0211 is equal to X squared divided by 1 minus 0.145. Now, when you push the buttons on your calculator, you don't get the same number to the correct sig figs. If we do that over here, and we do 1.000 minus 0.145, we get a 0.855. So it changes it, unlike the last time where it was the 0.019999 and you rounded it to 0.02. So this one is going to change. And so we have to get that, which we now know is 0.855, multiply both sides by 0.855, and then take the square root. And that will give you your X2 value, which is a 0.134. All right, now, as I stated before, your X1, and you'll know if you're making a mistake, your X1 is going to be your largest number. Your X2 is going to be your smallest number. And every number, then the next number is going to be higher than X2. The next number is going to be lower than that. And so it's going to go high number, low number, high, but not this high. This is the highest number. This is the lowest number. And so you're going to reach a point where it's always the same number. All right, so we only have to go until we get the same number 2 times. All right, so these are not the same number. And so now we plug this number in for our X value that we neglected. So we have 0.0211 is equal to X squared divided by 1 minus 0.134. All right, so now we plug in our 0.134. And then we get our X3 value. So when you take your 1.000, subtract your 0.134, here you get a 0.866. All right, and so you have your 0.866 here. Multiply both sides by 0.866, and then take the square root, and you will get your X3 value of 0.135. All right, now, okay, that's as high as it can get. Good, it didn't go higher than that. This is as low as it gets. Good. All right, so this number is between your highest and your lowest number. If it were the same as one of those numbers, you would be done. All right, it is not exactly the same, but now you know your answer is either going to be 0.134 or 0.135. All right, so we plug that in. So 0.0211 is equal to x squared divided by 1 minus 0.135. So we put that where we neglected the x, and now we have 0.865 is our number there. So when we subtract that, we get 0.865. Multiply both sides by 0.865, take the square root, and you get x4 is equal to 0.135. That is now your final answer. So it is the same as a previous answer, and therefore this is your final answer. All right, and if you do the quadratic equation, you will get exactly the same answer as you get when you do successive approximations. All right. So now we go back up and answer our question, because the question was, what are the equilibrium concentrations? So now we have our x value, and so we have the answer here, 0.135 molar for our PCl3. 0.135 molar for our concentration of Cl2, and our 0.865 molar when we take our 1 minus the 0.135 for our PCl5. And then a final step that you could do is you have your expression for Kc, you plug in your numbers, 0.135 for Cl2, divided by the 0.865 for PCl5, and you will get the 0.0211. Now, will you exactly get the 0.0211? Probably not. There are always rounding things that you're going to do, and then you multiply rounding things. And anyway, but it's going to be at least the 0.021, whether it's a 1 here or a 2 here, or if it's 09 or 08 instead of 11, whatever. But it's going to be very, very close to 0.0211. If it is nowhere close to that, well, then you know you have the wrong answers. All right, so successive approximations, that is the way that I will do all of these things. Quadratic equation, there are a lot more error possibilities when doing that. You will know when you have an error in this one because, again, your first number is the largest number, the second one's the smallest, then it's going to get larger than the second one, but not is the largest. So largest, smallest, and every number is in between there until you get two numbers that are the same. All right. So you'll know immediately if you're not doing something right. If you get a large number and then you get a larger number, you did something wrong. Largest number is first, smallest number is second. And if the first and second number are exactly the same, like our first example, that is your answer. All right, so I promised some which way does the reaction go. So let's see if I can find one of those. How about this one? All right, so let's go back to our CO gas plus 3H2 gas in equilibrium with CH4 gas and H2O gas. And the K value for that, Kc, again, for this one is 3.92. All right, and so what is the problem going to be? Well, it's going to be which direction will the reaction go? All right, and they're going to give you some concentrations. All right, so here's your initial concentration. This is 0.0200. This is 0.0200. This is 0.0010. And this is 0.00100. All right, so now we see that we don't have a zero. If we have a zero, we know exactly which way it goes. We can't have a zero. It would have to form a zero. When you have concentrations of all your reactants and all your products, then you have to calculate QC. right? If QC is larger than KC, so Q is too big, that means you have too many products, not enough reactants, it would go to the left. All right, and so if we wrote that, and we look at our QC versus our KC versus our QC, again, if QC is too large, that means that your KC is less than your QC is larger. If you write the KC value first in our less than or greater than, you will note that the less than or greater than will point you in the direction the reaction is going. So when the KC is smaller than the QC is too large, it has to go pointing to the left to get rid of some of the products. All right, if you calculate your QC and you see that it is smaller than your KC, so if your QC is too small, which means your KC is greater than your QC, if you write the KC first, it will point you in the right direction, because if your QC is too small, that means you have to go to the right to form more products to make it bigger. All right, so a good way to remember it, but you have to remember that in your less than or greater than, make sure the KC is coming first, and then your greater than less than sign will point you in the right direction. All right, your expression for QC, your expression for KC, they are the same. All right, so KC expression is exactly the same as Q. I put a C because we're doing concentrations. So that is your concentration of CH4, concentration of H2O, divided by the concentration of CO, and the concentration of H2 raised to the third. Again, biggest error here is people not taking that and raising it to the third. So we just plug in the numbers. Now, when we're plugging in these initial numbers, we are not looking at the KC. The KC is only at equilibrium. Anytime you are not at equilibrium, you are calculating a QC. So we are calculating our initials. So these are QCs, 0.00100 times 0.00100 divided by 0.0200. And 0.0200, here's where the errors always occur, raised to the third. All right, and so when you push the buttons on your calculator, you get a QC value equal to 6.25. All right, so again, you're going to compare it. Again, if you write the KC first and the QC next, all right, and then you put in your correct less than or greater than arrow. So KC is given, 3.92. QC is calculated. We just calculated it, 6.25. And we see that 3.92 is less than the 6.25. So if you're able to write in your right arrow, your less than arrow, you see that that points to the left. And yes, it's going to go to the left. Your QC is too big. All right, 6 is almost twice as big as it should be. All right, so that means that the QC has too many products, not enough reactants. And so it's going to go to the left to get rid of some products and get some reactants. All right, and so this one, the answer was, which way will it go? And the answer is, it will go to the left. It will go to form reactants. It will go in the reverse direction, however you want to say that it is going to the left. All right, so there will be problems just like that one, where you have to calculate your Q, compare it to the K, and determine which direction that it goes. And of course, if you calculate it and you got exactly the same number, so if your QC equals KC, you're at equilibrium. All right, so they could pick out numbers where they're actually at equilibrium, and you push the buttons and your QC is the same as the KC. Well, then it doesn't go in either direction. It's going in both. Rate of forward is equal to rate of reverse. You are in a dynamic equilibrium. All right, we're going to go through this one again, just to show you what they were doing. I was a little confused of what was going on. I just looked at it when I got back to my office and said, yes, that's what they did. All right, so when we did our quadratic equation with this problem, and note, okay, for this one, the KC is 49.7. That is not a small number. That is a large number. Not a greatly large number. It's not a huge number. But any number greater than 1 is considered a large number. You cannot do successive approximation. You can't say that you can neglect x because it's small, because it's not small. It's large. All right, so in the case of this one, there are other ways you can manipulate it. I would still do successive approximations, but there's more steps to it. Whatever I can do to not do the quadratic, I will do it. All right, so anyway, you can't do the quadratic in this case. You have your H2, which is 1 minus x at equilibrium. You have your I2, which is 2 minus x. And then you have your HI, all right, which was 0. And so when it at equilibrium, it was 2x. So we went through that last time. And then we did our setup. So our KC was 49.7, and that was equal to our 2x squared over the 1 minus x and the 2 minus x. And then I FOILed the bottom, and I got my, so when you FOIL the bottom, you get your x squared minus 3x plus 1, or plus 2, sorry, plus 2. And then I multiplied both sides by that, and I had my x squared minus 3x plus 2. And then I had my 49.7, and this is where the difference was, and that was equal to 4x squared when you square the top. All right, so this is where we were at yesterday, and then I distributed my 49.7 to my x squared, my 3 minus 3x, and my plus 2, and then I brought my 4x squared over, and then I had my A, B, and C, and I pushed the buttons, and when I got back to my office and got exactly the same answer that they did. All right, so your other choice here, instead of distributing your 49.7 and giving you such large numbers, they opted to divide both sides by the 49.7, which is absolutely fine. 49.7, and so the 49.7 here is gone. There it is gone. And then when you take your 4 divided by the 49.7, you get your 0.0805 x squared, and then you just subtract your 0.0805 x squared on both sides. So when they had this, we did that exactly the same. Then came this part where I was like, what in the heck? All right, so here again, they're going to FOIL this out and get the x squared minus 3x plus 2. Not sure why they didn't show what they got when they FOILed it. All right, and then when you take your 2x squared and divide by the 49.7, divided both sides by the 49.7, as I showed before, that gives you your 0.0805 x squared. Then you subtract 0.0805 x squared from both sides. Subtract 0.0805 x squared from both sides. And that's where you get your 0.920 x squared. Then you have your minus 3x, your plus 2. And this is your A, this is your B, and this is your C. Again, if you use the numbers that I had at the last lecture and you put it into the quadratic equation, it gives you the exact same solutions. You will get 2.33 and you will get 0.93. All right, so at that point, we have two positive answers. So a lot of times, one of the answers is negative, and one of the answers is positive, and you know right away that you can't have a negative concentration. All right, so here there's more to it. You have to always, you're going to have one valid answer and one invalid answer. All right, so when we had our 2.33, so remember we had 1 minus x and we had 2 minus x. for our concentrations of H2 and I2. If you take your 2.33, 1 minus 2.33 is a negative concentration. You can never have a negative concentration. 2 minus 2.33, also a negative concentration. All right, so your 2.33 answer is an invalid answer. It cannot be the correct answer. When you have your 0.93 and you have 1 minus 0.93, yes, that's a positive answer. 2 minus 0.93, yes, a positive answer. And so that is the X value. And so the X value is your 0.93. That gives a positive answer for your hydrogen, a positive answer for your I2. Either answer would have been a positive HI answer. And if you put that into your KC and you put in your negative number here and your negative number there, of course, a negative times a negative is a positive, you're going to get that KC value, but it is, you have to know you can never have a negative concentration. That is an invalid answer for this problem. All right, so successive approximations, you will be required to do at least one. You then will have options to do either successive approximations or quadratic equations for any of the others. Sometimes there's no choice. If you have a cubic equation, a quartic equation, you don't know how to solve those things. I had one student that didn't know how to solve it, but most people do. I don't know how to solve it. So I was like, how do you know that? I don't know how she knew that. But anyway, she couldn't do it on paper, but her calculator could do it for her. So she knew how to use her calculator to find the answers for cubic and quartic equations. All right, so the one in the book is here. All right, so the one that's in the book we'll do this one. All right, so let's do this problem. We're going to take HF all acids are aqueous. This is an acid. It is aqueous. We're going to add H2O. We're going to get H3O plus and F minus. And the Kc value for this is 2.0 times 10 to the minus 4. Initial. We have a 0.10 molar HF. Calculate the equilibrium concentrations. All right, and so the first thing that you're going to do is write the setup for Kc, and that will determine if you've got a chance at getting the problem right. It should be the easiest thing to do, but it is, okay, that's aqueous. And just like in chapter 4, if you have an ion, all ions are aqueous, but I will put aqueous for these ions. But if it has a charge, plus a minus charge, all of those ions are aqueous. All right, and so for our Kc, concentration of products over reactants, so we have our H3O plus, we have our F minus, we have our HF, and we have the error if you're putting in H2O. All right, so make sure that you're looking at the phases, and you must know that when you're doing a Kc, if it is a solid or if it is a liquid, water is very important to look at because for H2O, you will have it solid, liquid, gas, depending on the temperature. And so in this reaction, I'm running it at room temperature, and my H2O is a liquid, which means it is not included in the Kc. And so the initial concentration of H2O liquid doesn't make any difference. We know it's there because aqueous means that it's in water. All right, and so I didn't say anything about H3O plus, I didn't say anything about F minus. If there is nothing stated in the problem, then you didn't add any. All right, and so here we have 0.1 molar HF, and that was all that was stated. That means nothing else was in there. All right, and so we don't have to calculate Q. We know that it's going to the right. You cannot have zeros at equilibrium. So minus the coefficient of X plus the coefficient of X. We're not worried about water. It is not part of the equilibrium. Plus the coefficient of 1x. So then at equilibrium, we have 0.10 minus x. We have x, and we have x. Right? And so then we just plug it in. And so we have x times x divided by 0.10 minus x. And that is equal to 2.0 times 10 to the minus 4. And so here, unless it said you had to do successive approximations, you have your choice. You can have it as multiply it out, get your A, B, and C, put it into the quadratic equation. But I see that my Kc is small. Therefore, X is also small. Anytime you have a small Kc, the amount coming to the right is also going to be small. And so I always will choose successive approximations. For me, there is a lot better chance to not make a math error. When you are doing foiling and all that stuff and getting your A, B, and C, you would have to check it, double check it, make sure you didn't do anything wrong. Lots of places to make errors. All right, so here it just comes out to, I know X is small, I'm going to neglect this X, and I have X squared over 0.10 is equal to 2.0 times 10 to the minus 4. So when I multiply both sides by 0.1, I have X squared is equal to 2.0 times 10 to the minus 5. And when I take the square root, I have my X1 value, and that is 4 point something times 10 to the minus 3. And 4.5. So that is a 4.5 times 10 to the minus 3. All right, so I'm going to plug that in where it was neglected to get my x2. And so I have x squared over 0.10 minus 4.5 times 10 to the minus 3 is equal to 2.0 times 10 to the minus 4. And so I get that answer. All right, so when you do that, you get a 0.09955. All right, so multiply both sides by that. So 2.0 times 10 to the negative 4, and then take the square root. And you get 4.5 times 10 to the minus 3. All right, so you got the same answer twice, so that is the same, and therefore this is your final answer. All right, so 4.5 times 10 to the minus 3. So now you have to answer the questions. All right, so you have 4.5 times 10 to the minus 3 molar for your H3O plus. You have 4.5 times 10 to the minus 3 molar for your concentration of F minus. And then when you take your 0.1 and subtract, you get 0.0955. All right, so again, so you have two decimals. and then you subtracted 4 decimals. So you have 2 decimals minus 4 decimals. You give your answer to 2 decimals, and your final answer is 0.10. All right, because that would round back up to 0.10. And so neglecting x minus 4 is on the border. Sometimes it will take 3 x's to get a check. In this case, x2 was exactly the same as x1, and it was complete. All right, so this problem that we just did is going to be a problem in chapter 15 and 16, also in chapter 14. All right, and so when we get to chapters 15 and 16, it's going to then say, all right, here's an acid, 0.1 molar. Here's the K value for that acid. It's going to say calculate the pH of this acid. All right, and you're going to have the equation that pH is equal to the negative log of your concentration of H3O plus. So your pH is equal to the negative log of your concentration of H3O plus, and this is at equilibrium. All right, and so that is your 4.5 times 10 to the minus 3. And what we do know is that when you stick an acid in water, the pH is going to be less than 7. So you had better get a number less than 7. And so you plug it in your calculator. Negative, and it is the log log, not the ln log. It is the log base 10 log. Negative log of 4.5 times 10 to the minus 3. And that gives you a 2.35. The sig fig rules for taking the logs of numbers is very strange. All right, so pretty much I'm going to go 2.35, which is the correct number of sig figs to give for the pH. So what I would always say for the pH is don't worry about the sig figs, but you always give it to 2 decimals because that is right 99% of the time. All right, so you'll always give your pH to 2 decimals, not 3 sig figs, because if it's 10.35, again, 2 decimals. All right, so always would give your pH to 2 decimals. All right, we will pick up there on Monday. So lab tomorrow, I'm planning to put a video online today about your report sheet that is due tomorrow so that you can look through that video, make sure you have all your numbers correct. And then tomorrow we're doing the same reaction, but we're changing the temperature. And the report sheet is due tomorrow before you do your lab.